deviation off the mean. That's all that says. No deviation off the mean. Look at number 2. This guy, the second one. Your mean, your median, and your mode are still 5. There it is in the middle. Mean, median, and mode. Still 5. But look at the spread of my data. Now, we can kind of figure out the standard deviation by this. If I draw a simple curve here, it tells me between here and here, I should go out 3 standard deviations. I'm not concerned about you doing this, but just so that you kind of get an understanding. So from like 2 to 5, if I divide 3 by 2 by 3, if I have 3 units from here to here, so figure this is a 5, this is a 2. I have to fit 3 standard deviations in here. So my standard deviation is approximately 1. Does that make sense? If I have to fit 3 standard deviations in here. Kind of makes a little bit of sense. I'm not going to ask you to calculate it off of a graph. I'm just going to ask you to say how far it deviates off the mean. Is it more spread out? A larger standard deviation will be more spread out. This guy also, if we took the average of all these things, his mean is smack in the middle again. But look how spread out my data is. In this case, my graph would be out here somewhere. So now I have a lot more between 5 and 1, if you will. So if I go 5 or 4 of them, my standard deviation is a lot wider, isn't it? It forced my graph to spread out more. My data is more spread out. This just describes your data in terms of how spread out it is. What's the spread on your data? And that's the important part about a standard deviation. Oops. That's the important part. So for this example, without calculating, estimate the population standard deviation. They're all here. My n is 8, it means I had 8 entries. There's your frequency, 8. My mean is 4. This is my population. Everybody sits right here. My mean is 4. What would my population standard deviation be? 0. There's no deviation off the mean, right? Isn't everybody right there? If I made a frequency chart, what would this look like, my frequency chart? How many x values would I have? Only 1, a 4, and what would its frequency be? 8. I only have one data set, one data. X is 8. So did x deviate off of my 4 at all? No. So my standard deviation would be 0. Here's another guy. My mean is going to be smack in the middle when we average this. Again, I have n of 8, 4 and 4. But now, technically, my curve would kind of go like this. Estimate your standard deviation. Just estimate. Would it be 0? No, it wouldn't be 0 because they're not sitting all together. They moved off my mean. I have movement. My mean should be smack in the middle here. I have movement here and movement here. I'm a little bit off. So should it be a big standard deviation or a small standard deviation? Small movement off my mean. As opposed to this guy, here's my mean here. Look where my data went. All the way here, all the way here. Let me ask you this. Which standard deviation should be larger? This first one or the second one? The second one. Because isn't this more spread out? If I try to draw my normal curve, look how spread out my data is. So let's just estimate. So from here, from 4 to 1, I went 3 positions. How many standard deviations do I get? 1, 2, 3, right? So divide 3 divided by 3. What does that become? 1. So your standard deviation is approximately 1. Just approximately. I don't care what they say it is. We don't have to get any more detailed than that. If your standard deviation here goes from 4 to 0, we went 4 positions. This is a little bit more spread out in here. We would even be closer in here. We probably would be less than 1. And this guy is far greater than 1. We went 4 and we divided it by 3. He's going to be greater than 1. Okay? So you just kind of like get a feel for this. Just the more spread out it is, the bigger the standard deviation. Closer together, the smaller the standard deviation. Because what does the word deviate mean? Go away from. If you deviated away from your plants, say you had a bunch of plants, and you said, first thing we do this, then we do this, then we do that. You deviated from your plans. What did you do? You did something different, right? You moved away from them. You made it a little bit different. So standard deviation is how far does it deviate off the mean? Most of the time we're going to use your calculator to find it. We're going to put everything in your L1. If you have an L2, we're going to put it in your L2. We're going to do the one-pair stat. And remember, when we do your one-pair stat, whether you have one table or you have a frequency or not, this sigma, this is your population standard deviation. This S is your sample standard deviation. X bar represents a sample mean, but it is the same as your population mean. Right? So those are the important things I want you to remember. Now, I showed you yesterday your curve. I gave you your curve that you saw in Algebra 2, and I gave you the curve that we use in statistics. We have a more generalized curve because you're going to see pretty soon. We don't even go to the curve to find the percentages. We go to a table or our calculator. So right now, for our purposes, this is called our empirical rule. Okay, so we're getting away from yours, where you separated it by halves, and we're just moving to this. And these approximate this. It says between 1 and -1, you use about 68% of your data. It's actually 68.2 if you add up your percentages. But we're just rounding. So empirical rule says about 68%. And doesn't it make sense? Because isn't this the highest part of your curve? Like if you took sand and you made a sand mound like this, right? Isn't this where most of your sand sits, in the middle? And it just kind of tapers off to the side, right? So you pushed all your sand together and you went like this. So your sand piles high in the middle. So this is where it piles high, right in the middle. So 68% of my data is falling there. Okay. Plus or minus 2 says 95% of my data sits there. If I'm 2 standard deviations above, if I'm 2 standard deviations below, I find almost all of my data, 95%. In statistics, if it's plus or minus 2, if it's like plus or minus 2 standard deviations above or below the mean, we say this is unusual. Believe it or not, this is the words that they use. These are our big boy and big girl words here. If it's plus or minus 2 standard deviations away from the mean, it's unusual. It's extremely high or extremely low. So that's an unusual occurrence. If I'm plus or minus 3, then I almost have my whole entire curve. So plus or minus 3, 99.7% of my data sits there. If you think about this little tiny section here and this little tiny section here, add up to 0.3%. Adds up to 0.3%. We consider this, if it's plus or minus 3, very unusual. Because I'll hardly find something way out here or way out here. Now, remember yesterday, I did say we exaggerate our curve. Normally your curve, and you can see your book, they make it more this way because your 3 sits out here, your 2 is over here. If we did that, we wouldn't be able to fit anything on our curve. So we exaggerate our curve. We always make it a little bit wider. We make it a little rounder. And we can kind of see the 3 positions here. But realize that this little piece is this tiny little piece out there. Very, very, very small amount. Good? Am I boring you to tears today? Oh, yes. Okay. Standard deviation is always positive. That's how far it deviates off the mean. It's a distance off your mean. Yes, we get a -1 standard deviation away from the mean, a -2, but it's always measured in the positive. We're going to switch things around for you soon. All right. So if you look at example 6, let's try something. Maybe this will wake you up a little bit more. All right. It says in a survey conducted by the National Center for Health Statistics, the sample mean height of women, and I want you to start pulling out your information. This says sample. So sample, do I use an X bar or a mu? Think of that chart you wrote in your notes yesterday. Which one represents my sample? X bar or mu? Mu. X bar. With a sample standard deviation. Which one represents sample standard deviation? Sx or sigma x? Sx. Estimate the percentage of women whose heights are between 58.4 and 64.2 inches. Now, this is what you learned in Algebra 2. Same difference. We have 3 standard deviations to the left. We have 3 to the right. Put your mean smack in the middle. What is the mean? 64.2. So all I have to do now is add 1 standard deviation away, add 2.9. I get 67.1. 1 standard deviation away, I add 2.9. I get 70. Add 2.9. 72.9. When you go the opposite way, subtract. Take 64.2, subtract 2.9. 61.3. Subtract another standard deviation away. This is the easiest way to do this. Subtract another standard deviation. If you had had me for Algebra 2, this is how I do my standard deviations. Now, yours had all percentages in here. We're just going to use your empirical rule. We want to know what percentage went between 58.4, here's my 58.4, and here's my 64.2. I want to know the percentage of this. We could go to your other chart and figure out those percentages, or we can use your empirical rule. Your empirical rule says plus or minus 2 standard deviations is how much? What percent? 95%, right? Plus or minus 1 is 68, plus or minus 2 is 95. Did I use the whole 95? Did I use the whole thing? I used half of it. Just take half of this. So 47.5% of my data should fall between 58.4 and 64.2 inches. All we're using is your empirical rule right now. What percentage of your data falls between 64.2 and 67.1? I want here. That's one standard deviation above the mean. What does my empirical rule say for plus or minus 1? What percent? Look at your notes. What percent is plus or minus 1? 68%. But if I only went to the plus 1 and I didn't go to the minus 1, what do I have to do to 68? Divided by 2. Oh, 34%. Okay, what percent of my data lies between 55.5 and 72.9? Is what? 99.7. Very good. Very good, Sarah. 99.7% because this is my plus or minus 3. So we're kind of bypassing your old chart. Yes, we can't get in between right now, but we have a different way that we get in between. So right now we're just going to concentrate on this part of it, seeing how far off the mean this goes. Good. Questions? Questions, because we need to have it nice and quiet so we can go back to sleep? Okay. Now, this one's a little tough to get. This is called Chebyshev's theorem. Chebyshev says, well, data doesn't always fit a natural curve, right? So what do we do when it doesn't fit a natural curve? This is the only time we work with a non-normal curve. The only time. Chebyshev addresses this just this once and says, well, life is great if everything is a normal curve, if all your scores are normal. But what did I say about the scores in this class? Where do your scores lie? Are they normal? Do I get like an equal amount of high ones and an equal amount of low ones? No. Everyone's pretty much doing pretty high, right? So you really aren't following a normal curve. You kind of follow on the high side up here. So sometimes we can't use the 68, the 95, the 99.7. He came up with a kind of a little theorem here, but he only can handle when he's 2 standard deviations above the mean or below the mean, and 3 standard deviations. He doesn't have 1 for 1, he just has it for 2 and for 3. And 2, it's 75, and 3, it's 88.9%. It's all that we can get through this. Now, what he says is this. It has to be at least 1 standard deviation above the mean for his to make sense. So he says this. If you take a look at example 7, let's walk through one of the examples. And this is the only time we work with a non-normal curve. He's saying that the age distribution for New York and Alaska are shown in the table that I wrote down here. And he's showing this. Here's my mean, here's my standard deviation. He wants us to apply his theorem for 2 standard deviations above the mean. So he has a nice little formula. And all we need to do is this. It's either going to be a 2 or a 3. So we plug this 2 into here. So 1 minus 2 squared is 4. 1 minus 1/4 is 3/4. And 3/4 is 75%. Okay? So that's how we get 75% of his data will cover 2 standard deviations above and below the mean. And how will we find above and below the mean? We will say, pretend it's a normal curve. I'm only going to go up and down 2. Add 22.5, you get 61.3. Add 22.5, you get 83.8. Subtract it. Now, when we do this and we subtract it, we get a negative. But as far as we're going to go down is to a 0. Because we can't have a negative number in this age distribution, right? We can't be negative years old. So we're going to pretend it goes down to a 0. So between 0 and 83.8, 75% of the data will lie. Because really, it is not a normal curve. It is a skewed curve. I don't know anything about the curve. I don't know which way it's skewed. Obviously, it's skewed more towards the higher than the lower. But I don't know which way it's skewed. So I can estimate that 75% of my data will fall 2 standard deviations below the mean, 2 standard deviations above the mean. That's all we can figure out from his theorem. Makes sense? The only time we work with a non-normal curve, this curve is skewed, but we don't know enough about the information to say, well, where is it skewed? So now if we look at the other one, at Alaska has a mean of 35.3 and a standard deviation of 21.1. And again, it's not a normal curve. And we want to go 2 standard deviations above and below the mean. So again, you would make your curve. It would go 2, start with your mean here, add 21.1, God bless you, add 21.1, and then subtract 21.1. And remember, it's not going to be negative, it's just going to go from 0. So what is the percent from 0 to 77.5 years of age? I plug this 2 into my formula. And again, this is 75%. You're only going to get 2 of them. One is a 2, one is a 3. And 3 is the 88.9%. That's all he can estimate. Because we don't know anything else about the skew. Okay? The only time we work with a non-normal curve. The rest of this is pretty much putting it in your calculator. We'll use your calculator again. We're going to use they talk about using your calculator, and we're going to use your calculator to find your standard deviations. Do we have to worry about figuring out a formula? No, but the difference here is this. Your other formula said this. Take the sum of the squares and divide it by n minus 1. The only difference is this. This is a frequency. So the only difference you have to worry about is this is your L1, this is your L2. And when you do a one-bear stat, you just have to say L1, L2. That's all you have to say. I'm not asking you to do another standard deviation chart with this. I think they do one. If you take a look at page 90, they do one using the frequency. Kind of similar to ours yesterday, but the first thing they do is, before they take the difference off the mean, they just multiply the x times the x. I'm not asking you to do one of these. I just want you to be aware that if you have a frequency, that's the only difference. And then we calculate the difference off of that. But you're going to use your calculator. So really, not a big deal there, right? Calculator from here on in. And again, sometimes we have an interval. And what do we use when we have an interval? Midpoint. Calculate your midpoint, and then the rest of it works the same. L1, L2, and you have a one-bear stat, L1, L2. So you're going to be using your calculator through this. I wanted to show you yesterday how the standard deviation is derived, just so that you know. And if you take this in college, you may be asked to do it by hand. They may ask you to do it by hand as well. This way you kind of had a little bit of exposure. Good so far? Okay. The last piece of information that I need to give you for this is called coefficient of variation. Your coefficient of variation is a little bit different. You don't use this too much, but you will see this in some business things because you want to know like what made this vary so much. It's pretty simple, the formulas. And again, in statistics, when you have a formula on the test, I give you the formula. Because I figure in real life, are you going to really remember this when you walk out of here tomorrow or at the end of the year when you don't have to do this anymore? No. My biggest thing is for you to learn how to apply it to the formula. So you could at any time Google, what is the formula for coefficient of variation? And it will give you the formula. I need you to know why we use it and how we use it. You can Google it anywhere you want to. And if you take this in college or you take this, like you major in this or you use this in the business world, most of the time you don't even use the formulas anyway. You're in Excel sheets and they're all there. All the formulas are all in Excel sheets. You use whatever software they use and it's all in their software. Basically you input your data, you tell it what you want and it does everything else for you. So the coefficient of variation is used to compare the variation in different data sets. For instance, if I give you a test in here, and I look at the variation of how your tests differ, and you take a test and you say you're all in the same science class, you take a test in your science class, and you do the variation there, should I really be comparing those variations? It's kind of hard for me to compare them because it's not my course. It's a different course. So instead, we have a way to find a coefficient of variation so that I can compare those coefficients and then see where they stand. Basically, a coefficient of variation is very simple. All you have is two things to calculate, a mean and a standard deviation. If you're a population, you're the population mean, the population standard deviation. If you're a sample, you're the sample mean, sample standard deviation. How does that standard deviation compare to that mean? So when I look at your statistics class, how did your standard deviation compare to this mean? I look at your physics class, how did that standard deviation compare to that mean? Once I find those coefficients, then I can say which coefficient was greater, which one was less. And because we're comparing them, it's easier. You multiply by 100, so therefore you get a percent. That's all this says we're going to do. So let's take a look at just one of these. Hang in there with me, guys. We're all falling asleep on me today. I told you this is still a little dry till we get to chapter 3. So this table shows the population heights and the weights. So population means we're using mu and we're using sigma. Okay, heights and weights. Find the coefficient of variation for the height and the weights. Normally, you guys probably did a linear regression to compare what relationship do we have between heights and weights of people or whatever we're measuring. So this is a little bit different. This is going to be an L1. This is going to be an L1. So I need this half of the class to figure out the mean and the standard deviation for the heights. I need this half of the class to put it in your trusty calculator, find the mean and the standard deviation for the weights. This is not an L1, L2. They just gave it to you in one graph. I want to know how they relate to each other. But I really have no way of saying now, a height of 52, a height of 72, a weight of 180. What does that mean to me? So if I look at their coefficients of variation, I should be able to compare them. Which one was more relative to the mean? So let's put this for the height. Remember, I want the population standard deviation. An easy way to remember this formula also is which way you're going to divide. You're only given two pieces of information, the mean and the standard deviation. If you divide the other way around, your percents are over 100. So really, you don't want your percents over 100. Because if I divided the larger number by the smaller, and then multiplied by 100, that'd be a pretty big number. I always got to do the small divided by the large. So it kind of gears you to that. Did this group find me a mean and a standard deviation? A mean? 72.75, so we'll make it be 72.8. Did you find me a standard deviation? Okay, so we'll make it be 3.3. Because this is one more number than our data. Okay, this group over here, did you find a mean? 187.8. Good. And how about a standard deviation? Population? Stephen? 17.7. Sounds good. We're going to keep it one decimal. Since our data doesn't have any decimals, our rule of thumb, one decimal more than our data. Okay, so now all we have to do is apply this to this formula. The smaller number divided by the larger number times 100. The smaller number divided by the larger number times 100. This gives us our coefficient of variation. So this guy comes out to be 4.5%. You could see this one's larger, right? Because this is larger compared to this one. That's real small to compare to that one, but even compared to this, it's a lot larger. This is 9.4%. So now, if I look at these percents, this tells me which has more variability. Which one varies more, the weights or the heights? What would you think? The weights. The larger the number, the more variability. So we could say that the weights vary more than the heights. The weights have a higher variability than the heights do. Think about real life. Isn't that true? Aren't you pretty much like, especially for girls, not so much for boys, but especially for girls, aren't you pretty much the same heights? Just a little bit different in heights? But don't your weights vary a lot more? Like boys, your heights vary a little bit more, but you know, pretty much common, but your weights vary a lot more. Okay, so the weights have more variability than the heights. Makes more sense, doesn't it? So if I'm going to compare two tests, my test versus your physics test, whichever one has a higher rate, means the grades in there vary more. That's all it means. I'm able to compare two things that I wouldn't normally be able to compare. So have I bored you enough for one day? Yeah, Chris says yeah. Thanks, Chris.